Okay, so here's the next step in the review. We have our balanced chemical equation, and the question is asking us which reactant will be consumed first. Remember that an equation is broken down into two parts. On the left, you have your reactants, and on the right, you have your products. So if the question is asking for which reactant will be consumed first, then I'm looking at this guy's on the left side over here, which are the reactants. Now, it's going to be one of these two compounds. So because we're working with these two compounds, right? Then what we're going to do is we're going to use the mole ratio that exists between these two compounds. So the first thing I got to do is I got to find the mole ratio. Let's see here. Okay. I got to find the mole ratio. I don't know why my thing's giving me a hard time. But that's where we start. Okay. Now, the mole ratio is easy. The mole ratio is just looking at the ratio that exists between the coefficients of a balanced chemical equation, but specifically those compounds. Okay. So the easiest way to do it is to say, okay, well, the mole ratio then is the fraction between this compound and this compound. Okay. I don't know why my iPad is giving me a hard time, but there it is. Now, you cannot write it just as a simple fraction, okay? It has to be written in expanded form. So what do I mean by expanded form? What I mean is you need to write it as 4 moles of ammonium phosphate over 3 moles of lead for chloride. Okay, it has to be written in this way. You need to make sure that you include this and this. It's got to be complete. Now, when you're talking about mole ratios, you can write it two ways. The first way says that you can write it as 4 moles of ammonium phosphate over 3 moles of lead for chloride, or you can write it as 3 moles of lead for chloride over 4 moles of ammonium phosphate. Now, we're doing this because we're trying to calculate which one of the reactants is going to be consumed first. What we're looking for, right, in this case is the limiting reactant. Remember that the limiting reactant is the reactant that limits the amount of product because it's the one that runs out. So because it limits the product, it's called the limiting reactant. Now, we're going to use the mole ratio and we're going to do the calculation, okay? We got to take a couple of steps first, though. We got that out the way. Let's go take a look at the original prompt. I'm going to scoot over here a little bit, okay? All right, so it says that we have 0.85 molar at 300 mils, okay? And that's combined with 150 grams of lead for nitrate. Okay. All right. So let's take a look at that. Let's write that down. 800 mils. Sorry. 0.85 molar at 300 mils. And then we have 150 grams. Okay. So this is for ammonium phosphate. And this is for lead 4 chloride. Okay. Now, we're going to use the mole ratio, right, to figure out this calculation. But there's a problem. This value and this value, the question is, are they in moles? Okay. Are they in moles? So this gives me a molarity, right, which is a solution. So I have here a molarity. And this gives me grams. What I don't have is moles, right? So the answer to this question is no, I don't have moles. Now, why is that a problem? Well, if you take a look at the mole ratios, all of these are in moles. And we use the mole ratio to cancel one unit and convert to another. So if we don't have moles, then we can't use mole ratio. So then what do? Well, the next step is convert all values to moles. Right? We have to convert all values to moles. Now, let's start with ammonium phosphate. Okay, ammonium phosphate has 0.85 molar at 300 mils. Okay, so anytime I see this unit, right, this is what I'm thinking. I'm thinking of a molarity, right? It's a solution. So because it's a solution, I have to use the molarity formula. The molarity formula is going to allow me to convert into moles. Remember that this is your volume. This represents the moles. And this represents the molarity, or the concentration. Okay? So because I have the values, I know I have two of these values. So what do I have? Well, let's see. Molarity at this point is 0.850 molar. Moles, we don't know. That's what we're looking for. And liters is in the volume, which here is 0.300 liters. How did I do that? I took my decimal and I moved it over 3 times because I know that 1 liter equals 1,000 milliliters. You can set up the conversion if you need to, but moving the decimal would be sufficient. Okay. Now, remember, guys, if at any time I'm going too fast or you have to rewatch something, you can do that. Pause the video, go back, watch it again, and then give yourself time to write. Okay, so if I'm looking for N, then I'm going to take this formula, right? And I'm going to manipulate it so I get N by itself. I'm going to multiply by liters on both sides, right? I'm multiplying because moles and liters are being divided, so the opposite of division is multiplication. When we were going over this topic the first time, a lot of you guys were trying to add and subtract. Remember that if you want to move something over to the other side of the equal sign, you have to do the opposite operation, right? It's not the same thing all the time. If you're adding and subtracting, then you add and subtract to move the other way. If you're multiplying and dividing, then you have to multiply or divide. It's very, very simple. Okay, so now that I have this, my equation looks like this. To find the moles, I'm going to take the liters and I'm going to multiply it by the molarity, right? So let's go ahead and plug everything in. I'm going to replace these two variables with the values that I have in the problem. So to calculate moles, I'm going to take liters and I'm going to multiply it, in this case 0.300 liters. I'm going to multiply that by 0.850 molar. Okay? All right. Now, let's take a look at what happens. If I multiply these, I end up with moles being 0.255 moles, right? Which is represented by N. Okay? All I did was take these two values and I multiplied them in my calculator. So what this tells me is that I have 0.255 moles of ammonium phosphate. Now, this can be written as moles with the N, or if you want to match the mole ratio, you can write it as 0.255 moles of ammonium phosphate. Do you see how now it's starting to look more like the mole ratio? That's what we want, okay? So let's go ahead and box this in, and we'll come back to it in just a minute, okay? If you need to, pause the video, catch your breath, and we'll keep working. Okay, the next one is 150 grams, okay? We have 150 grams of the lead 4 chloride, okay? So I'm going to write that down here, 150 grams of lead 4 chloride. Okay, now I can't use molarity here, right? Because I don't have a solution. I can't use Avogadro's number because I'm not working with molecules or particles. What I do see is grams, right? Grams is a unit of mass, right? It's a unit of mass. So anytime I see the G, that is my red flag to say, hey, I'm going to be working with some sort of mass. Grams equals mass. Now, if you're working with an element, then that equals the atomic mass directly from the periodic table. If, however, you're working with a compound, then in this case, you have to use molar mass. Okay? I'm not going to go over molar mass in this video. Go ahead and refer back to the video in your Google class on how to find molar mass because I'm trying to make this one short. So I'm just going to give you the molar mass. The molar mass of lead 4 chloride, I'm going to abbreviate molar mass, is 349.01 grams per mole. Okay, another way to write this is to say that 1 mole of lead 4 chloride has a mass of 349.01 grams of lead 4 chloride. Okay, again, there's a video on how to find molar mass. I'm trying to save you guys a little bit of time, so I'm not going to go over that right this moment, but feel free to go back and take a look at that video. Go ahead and erase this so I have space to work. Okay. Now, here is where we start, right? We have 150 grams of lead 4 chloride. I'm going to put that over 1. Then I'm going to multiply by my conversion factor. This is your conversion factor because if you look, there are 2 units, right, that are equal to each other, 2 different units. So what you need to figure out is which one of those units do I put down here at the bottom, okay? The answer to that is easy. Whatever unit you have here has to match the unit at the bottom. Now, do we have moles of lead 4 chloride or do we have grams of lead 4 chloride, right? So we have grams of lead 4 chloride, so I'm going to put the grams of lead 4 chloride at the bottom. Grams lead 4 chloride. If the grams go at the bottom, then the moles must go at the top. Now, what happens here is that the grams are going to cancel themselves out, and the only unit left is going to be moles. So let's multiply straight across. 150 times 1, because it no longer has units, becomes 150 moles of lead 4 chloride. 1 times 349.01 becomes 349.01. Again, the units here canceled, so 349.01 no longer has a unit. It's a standalone number. Now, what I'm going to do is I'm going to take that and punch it into my calculator, right, which is 150, and then I'm going to divide because a sort of fraction is a division problem, right? So you're going to divide that out, and what you're going to realize once you put it in is that you're going to end up with 0.42987. And everything here is to different significant figures because I've been lazy about my sig figs. So make sure that you either pay attention to the significant figures and all the values. If they're kind of all over the place, like my work has been, 4 is always a good number to start, okay? If otherwise specified, make sure that you pay attention to that because I may just ask you to give me the answer in a specific number of significant figures. But I'm going to go with 4. So if I round this up to 4 sig figs, that's going to be 0.4298. And this is going to be moles of lead 4 chloride. Okay? So that's where we're at. So now we have moles of lead 4 chloride, and now we have moles of ammonium phosphate, right? Now that we have these values, now we can begin to do our problem. So I'm going to use the empty space here in the middle, okay? And then I'm going to pick one. I'm going to just pick one. So I'm going to just pick 0.255 moles of ammonium phosphate. Okay? Then I'm going to put that over 1. Okay? Now, here's the tricky part. I need to pick the correct mole ratio. I want the mole ratio that's going to have moles of ammonium phosphate at the bottom. So let's go back up and take a look at our mole ratios. They're right here. Which one has the mole ratio at the bottom? The mole ratio with ammonium phosphate at the bottom, and the answer is this one, right? That's why I write both, so I can, doesn't matter which one I pick, I have my mole ratios ready. So we're gonna take that mole ratio and we're gonna write it right here. So 3 moles of lead 4 chloride over 4 moles of ammonium phosphate. So there's your setup. Once again, because we set it up in this way, moles of ammonium phosphate are going to cancel. Then we just multiply everything straight across, okay? And then we divide at the end. So 0.255 times 3. Let's get that one done first. Now, remember that because the units canceled, there is no longer a unit on that 0.255. All I'm going to do is multiply that by 3. Now, when I do that, I end up with 0.765. This unit is still here, so I'm going to carry over that unit. Moles of lead 4 chloride. Okay? This number down here no longer has a unit, right? So it's just going to be 1 times 4, which gives me the value of 4. If I take 7.65 and I divide that by 4, I'm going to end up with 0.19125. If I want that to 4 significant figures, I'm going to take this to 0.1913, and that is moles of lead 4 chloride. Okay? That is moles of lead 4 chloride. So I've used the mole ratio and I've converted from moles of ammonium phosphate, and I've taken that number or that value and I changed it into moles of lead 4 chloride. That's how mole ratios work. They allow you to convert from moles of one compound to moles of another using the mass relationships that exist within a balanced chemical equation. Now, what does this mean? Well, this value of the lead 4 chloride, this is my need. So what you've done is you've calculated how much lead 4 chloride you need in order to run this reaction. Now, why does that matter? Well, if I need 1913 moles of lead 4 chloride, this is how much I need. I'm going to compare that to this number, right? Because this is how much lead 4 chloride you actually have in the reaction, because this is the 150 grams that we started with, right? So 0.4298, 0.4298, sorry, moles of lead 4 chloride. This is actually how much I have. That's why you need to find moles of both, right? So now I got to figure out, okay, do I have more or do I have less than what I need? Well, I can see that this number is bigger. So in this case, my have is greater than my need. So if I have more than what I need, then lead 4 chloride is the excess. And if lead 4 chloride is the excess, then ammonium phosphate must be the limiting. You don't have to do both. It doesn't matter which one you do. If one is the excess, the other is the limiting. If one is the limiting, the other is excess. So which reagent will be consumed first? ammonium phosphate will be consumed first. I know this was a bit of a long one, but that's why I'm trying to separate this into multiple videos. Take a look at it, rewatch it, send me any questions either over email or directly on Google Classroom. I have my phone on me all the time. I may not get to you right away, but I will get to you, I promise. Go ahead and take a look at this, and then I'll set you guys up another video shortly.